I should not forget to. Yeah,
Shall we resume? Okay. Okay. Hello, everyone. The next speaker will be Carol. He will talk about the Hamiltonian cycle enumeration.
Yeah. Thank you. Thank you. Hello, everyone. Yeah. So this will be a talk on graphs and Hamiltonian cycles in graphs. So yet again, another topic for today. Let me start with what that actually means. So a graph is some vertices, and some of them are connected by edges. And this, for instance, for graph theorists, this is a dodecahedron. Maybe not for geometry, but for us this is okay. And in red you see a particular subgraph. That's what we call a Hamiltonian cycle. So a cycle is something going vertex, edge, and so on, closing, not allowed to repeat anything. Yeah? We've seen the definition of path in the first talk. And if that path closes and you visit everything, that's a Hamiltonian cycle. Is this okay? Is this clear? Yeah. So the dodecahedron is what we say. We say it is Hamiltonian because it has a Hamiltonian cycle. We say it's Hamiltonian. Okay. And now I really won't do algebra today, but I did want to do a little bit. So how many Hamiltonian cycles does it have? And it seems that under the full symmetry group, all Hamiltonian cycles lie in a single orbit. I give you that information. And a single Hamiltonian cycle has stabilizer of order 4. So maybe now you know how many it has. The full symmetry group is 120, right? So then you divide and you get it. So this one has 30 Hamiltonian cycles. I'm afraid that will be the only bit of algebra that I will do. And why is that? So why so I was in an interview for a postdoc fellowship and they asked me, why don't you do more algebra? There were quite a few algebraists in the jury. Why don't you do more algebra? The issue is that the vast majority of graphs that we'll be looking at have trivial automorphism group. Yeah, algebraists, they usually in some ways they exploit the automorphism groups, the symmetries there. But yeah, we are interested in things that come more from the graphs more naturally, and then you usually you don't have any automorphisms. So yeah, it's difficult then to really apply that beautiful, strong algebraic machinery. Okay, that's just a comment. Okay. This clicker doesn't help me. So yeah, this is what I want to talk today about, the meta conjecture a la Bondi. Now, there is in Hamiltonistic theory something called Bondi's meta conjecture, and this is from the 70s. And Adrian Bondi proposed the following. So this is Bondi's meta conjecture. I think that's 70s. What is that? So 70s. Yeah. So you have some non-trivial property P, and it implies the existence. So it implies the existence of a Hamiltonian cycle, G Hamiltonian. So again, that means you have a Hamiltonian cycle, yeah? G Hamiltonian. Now, Bondi's meta conjecture states that if this is true, then P actually implies that G is pancyclic. So that means there exists K cycle for any K. So Hamiltonian just means there is an n cycle. N is always the order for me, the number of vertices. Oh, can go back here. So here, so there is a cycle for all of the vertices. But Bondi says, well, if your property gives you this, it actually will already give you pancyclicity. Now, this doesn't mean that if your graph is Hamiltonian, it will be pancyclic. Obviously not. There are no triangles here, right? This is a different thing. So you want something non-trivial here. You will also notice the word meta here. He was himself aware that this is not really true in many cases, right? So first thing, this P needs to be a non-trivial property. Otherwise, you just give me, well, your graph should be connected and two regular. That's just a cycle, right? The cycle is Hamiltonian. It's all that it is made of, and it's clearly non-pancyclic. So see, he says, yeah, give me something non-trivial, okay? And there's another thing he says. There might be some exceptions, but they're easy to describe. This is Bondi's meta-conjecture. And it was very influential because I think also due to its vagueness, and people really like to prove the edge cases and see what happens. You know, sometimes some cycle lengths, only a few are missing here. I will talk a little bit about that.
Cycle, you mean you cycle k times to different paths to show the probability.
So this, for instance, this is the 5 cycle. 1, 2, 3, 4, 5. This is a 5 cycle. This is the boundary of the face here. This is a 1, 2, 3, 4, 5, 6, 7, 8 cycle. This one. So it's vertex, edge, vertex, edge, vertex, edge, and you close, and everything once.
So if that was pan cycle, there would be a 4 cycle and a cycle.
Exactly. So this means 3 up to n. Right? So for instance, the tetrahedron. Yeah, it has 3 cycles, it has 4 cycles, and 4 is, you can't go higher than 4. So that's pancyclic. Any complete graph is pancyclic, of course. But this goes much further, right? Bondi essentially says, yeah, except for some small cases that we can deal with, if your property gives Hamiltonicity, if it will give pancyclicity. Yeah.
So what qualifies as a property? Because you couldn't say P is just Hamiltonian.
No, yes, it's a good question. I don't think he specifies it. So it is really, but for instance, a good property would be large enough minimum degree. That's classical. If your minimum degree, so the degree is the number of edges that are incident to a vertex. So this is, for instance, 3 regular, all vertices have degree 3. But if you increase that sufficiently, your graph will become Hamiltonian. It's a classic theorem, easy to prove. And that's also what he picks up, and he says, well, except for those very exceptional graphs, they are pancyclic. Yeah. So such properties he had in mind. And is this okay? I know it is vague. It is supposed to be a little bit vague to, yeah, inspire, I think, guess work, some other work, and it actually worked. So, so let me propose also a meta conjecture. I'm trying to be a bit more precise than Bondi. So again, same setup, right? First part is the same as in Bondi. And then I say that then these graphs from some family of all graphs satisfying this property contain at least f of n many Hamiltonian cycles for some interesting function f. It should be non-constant, I hope, generally, and try to make f asymptotically best possible.
So it's the number of points.
Indeed. The vertex is indeed the point. Yes. Yeah, so it's essentially, it says if you have one Hamiltonian cycle, there should be in some sense many. That's what we're interested in. Let me give you a few. I want to talk today about a few examples of this, depending on also on how slowly or quickly I go. There's a related problem here. So given a natural structure condition imposing the presence of one Hamiltonian cycles, how many more must there be? So this is John Sheehan here in 75. This is one of the most famous incarnations of this particular problem. So you have a 4 regular graph. So every vertex has degree 4. And you impose the presence of one Hamiltonian cycle. Must there be a second one? Very difficult problem. There is a beautiful proof of Thomason using kind of a really ingenious combination of deterministic and probabilistic arguments that if you do, I think, 72 regular or something like that, there must be a second one. But he also proves that you cannot push it down to 4 with this technique. So yeah, it's open. This one, if you can do it, it would be very nice. So, but it's kind of in this flavor. It's a kind of a problem that is related. Yeah. So, and we will talk a little bit also about such problems. So let me give some examples in which we can make some progress on the f's, on the functions. Yeah, Hamiltonian cycles and planar graphs. Hassler Whitney, great American geometer, when he started out, he proved some things in graph theory. He then quickly moved to more serious parts of mathematics, but we are still left with some very beautiful theorems of his, and one of them is this one. So you have a triangulation of the sphere, yeah, and the only condition imposed is that you don't have separating triangles. So it means a separating triangle is a triangle with stuff inside and stuff outside. And Whitney says you don't allow that. Yeah, that's what full connection means. Then this has a Hamiltonian cycle. This is a statement. Is that okay?
Why is it for connected?
For connected is a notion from graph theory. I can go into the definition if you like. So it means that you cannot remove three vertices and disconnect it. That's why it's for connected. Equivalently, by Menger's theorem, between any two vertices, you have four internally disjoint paths. But it's equivalent in a triangulation to saying that you don't have a triangle with stuff inside and stuff outside.
That you said before that every vertex has four.
No, that's different. That's degree. This is connectedness. Yeah, there is some relation, but it's not the same thing. So yeah, and if you look at this, so this is an existence theorem. How many Hamiltonian cycles must there be? Because you quite quickly notice that there might be quite a few, but how many? And I don't know exactly how this continues. Let me see. Yes, this was strengthened. So Whitney and Tutte in the 50s showed that actually it's not important that these are triangulations. So planar four connected graphs are also Hamiltonian. This is stronger than this. So yeah, this allows other face sizes as long as you stay four connected. And here I mean triangulations of sphere. Every time I write triangulation, I don't mean of some other surface. I mean triangulation of the sphere. Yeah. Is this also okay? Yeah. So this is a stronger version of this. Planar four connected graphs also contain Hamiltonian cycle. Same question here, how many?
They are just two dimensional.
Planar indeed.
Everything else can be dimensional.
Dimension doesn't make so much sense for us, but planar just means that you can draw the graph indeed in the Euclidean plane without edge crossings. Yeah. And there's Kuratowski's theorem which characterizes these, but I don't want to go into that. But so that was planarity. You can find a drawing without edge crossings. And then the four connectedness we discussed. Okay. So this is one such enumeration theorem, Hakimi-Schmeichel-Thomassen, that we have n over log n Hamiltonian cycles in these four connected triangulations. So this is kind of the first step. We have Whitney, which said 1. We have actually n over log n. Let me give a brief sketch of the proof. So this is my sketch. Let this be the number of Hamiltonian cycles. Now this is the order. Alpha shall be the following. So visible, yeah. So in these four connected triangulations, we have something called, I think Colin called it the theta graph. The theta graph is for me something slightly more general. So this kind of structure, two triangles sharing this part. This is, I call this a diamond. There are lots of diamonds here, linear number of diamonds in these graphs. It's not difficult to see. Okay. There are some, I'm skipping over some details, but that's the main point. And then there is a whole theory which was invented by Whitney to show that the whole machinery to show that there is a Hamiltonian cycle which goes through a diamond like so. So this is, you need a lot of effort to do this, but you can do it. So there is a Hamiltonian cycle which goes through any diamond you pick, yeah, one specific diamond, you can go through it in this way. Okay. So aren't we done? We have a linear number of diamonds, lots of diamonds. And for each of them, we can traverse it like so. No, right? Because the same guy might cover many of them. The same Hamiltonian, that's the issue, right? The Hamiltonian cycle does something, comes back and covers your this particular shape here also. Right? So, but this is still true if alpha is the number of diamonds. Do you agree? Yeah.
Are they separate or are?
Yeah, the disjointness is a bit tricky, but I don't want to go into this a little bit. Yes, it's a good point. There are graphs in which you need to be really careful about how they overlap, and yeah, but let's talk about this case. Yeah, you can imagine like for instance what's something that is called a double wheel. So you have one vertex here, and a cycle here, and that's all the graph. And you connect these two vertices to everything on the cycle. Then these diamonds will have to overlap, and then you need to be careful. So, but this is sufficient. Like for the generic cases, we can think of this. But yeah, it's a good point. They might overlap a little bit. We need to be a little bit careful. But if we assume this, we have Hamiltonian cycles traversing them, but then this is true, right? If we divide by the number of diamonds, this is okay. Right? This is H is at least n over alpha. Right? Because we just get rid of what we double count if one Hamiltonian cycle goes through several. Yeah. That's clear. So Hamiltonian cycles. This is my graph, and this guy, this red guy, will visit these also. It's Hamiltonian. It must. And it might visit them just in the way that I picked, just that kind of shape. And maybe it does with the first three. Maybe there is one which covers like a linear fraction, right? So then we divide by a lot here. That's bad for us. But this is also true. H is at least 2 to the alpha. Why? Well, we can flip this around here. Right?
Yeah. What any change?
Number of Hamiltonian cycles. So we can flip this to this. All the rest stays the same. I just locally flip and I get a new Hamiltonian cycle, right? This is clear. So H is at least 2 to the alpha. So from this, you get these inequalities. That's easy, right? This is base 2 logarithm here. Shouldn't be a problem. Yeah, this is already there. And from this, it's easy to get this. H log H is at least n. And from this, it's actually also any large language model can do this quickly now to get this. This H is at least this. From here to here. And this is essentially this proof. That you have n over log n. So this is kind of the first bound for our f. Yeah. It's okay to continue. So this was improved. Bringt man zu viel van Klinkert to omega n or linear. Yeah, they got rid of this. Don't need to divide anymore by the logarithm here. And this is basically an extension of this technique here in a more general framework. This is a counting-based method that they introduced for this, and I think it has a lot of potential also. We use it also for some other results, which I might. It's the time to mention. Yeah, I'm going too slowly, but I think we have also already heard a lot of interesting mathematics. So let me just try to show you what I can. I don't want to go too fast. So this is n over log n, and this is n. Okay, and we can continue doing this. So this has been strengthened in several directions. So these authors, Liu, Wang, and Yu, and for Chinese authors, I usually also put the first name because I know at least 3 really good graph theorists called Yu. So, you know, it wouldn't say much if I just write that. So I put the first name there. They show quadratic, and this is asymptotically best possible. So the story here is actually over. Yeah, for the meta conjecture. So they should n squared. It's some constant and so on, but yeah. This is the graph that I mentioned. This is called a double wheel. You have a large degree vertex here, and a cycle here. You connect them like so. And this clearly has quadratic many Hamiltonian cycles. And this is actually conjectured to be the minimum, but that's very hard to show. But there's a certain polynomial, right? Quadratic polynomial, but maybe also not terribly interesting. But that this is asymptotically best. So this is I mean the lower bound that they could push it to quadratic. That's really nice, and it's a significant effort to do this, but yeah. So this is done. We know it for 4 connected triangulations. We know it. So maybe some two related results here. If you go to 5 connected triangulations and you cannot go higher than this in the plane, it's easy to see. So 5 is the most connectivity you can have. Then you have an exponential number. Well, it's also a bit nice here that you have this. They are denser, right? So you'd expect more, but there's really a qualitative shift here from quadratic to exponential. And then I like this theorem also because it's this last one here, because it kind of shows that the 5 connectedness is not the main thing here. The magic somehow happens before, because they show that 4 connected triangulation was at most linearly many 4 separators. So these are, again, sets of 4 vertices which disconnect the graph. These are 4 separators. They have exponentially many Hamiltonian cycles. So this is stronger than this, right? And so already for 4 connected, you have lots of triangulations which have exponentially many, but still such guys exist because they have very many 4 separators. So that's kind of, you need to encode. That's the story has to do with the 4 separators. How many Hamiltonian cycles you get. That's maybe you can see them as a kind of a bottleneck in the graph. Yeah, very vaguely said, but they show that it's not the 5 connectedness. You can go below 5 connected and still have exponentially many, as long as you don't have too many 4 separators. But if you really allow anything, then quadratic is best possible. Okay, so there's a second direction in which this was extended. So there is a constant C such that in every 4 connected triangulation, for any k, there are C and many k cycles. This is a sort of combination of the 2 meta conjectures, right? So it goes to pancyclicity like Bondi, but it also enumerates. So you actually have a linear number of k cycles for any k. Well, this is joint work with Solomon Low. And I could talk about the strange theorem here, but it's a little bit technical. I will not have time to show you other stuff, so I don't want to show it to you. There's a third direction. We skip it. Yeah, maybe I should just say, so you might wonder about Tutte's theorem. So there we only know about linear. So for Tutte, it might be that quadratic is also the best possible, but we can only show linear. So this extension, we don't have it to quadratic. We don't have it yet for planar 4 connected graphs, only for triangulations. Many arguments are much easier for triangulation because you essentially have all the edges there. But here you don't at all. You might have very large faces, arbitrarily large faces indeed. So it's more difficult. Okay. So I think, yeah, cycle double covers. I won't talk also about cycle double covers. This will go too far now. Some application to, I don't know if you're interested in cycle double covers, there's some connection to more topological problems, but it's kind of an application of what we're seeing. Okay. Let me talk about another topic where we apply this research program. This is a meta conjecture. Yes. Hamiltonian cycles in what are called S, T graphs. And let me show you, there is a certain dichotomy theorem I want to show you first, and then I will go into a very specific case. So for graphs G and F, we say that this graph G, the host graph G, is F3 if G does not contain F as an induced subgraph. What does induced subgraph mean? We have some big graph G, and say you take some vertices in this graph, then you look at the edges that are present in G between these vertices, and that is the induced subgraph. Yeah? You take those and you say F3. So for instance, F might be K3, your triangle. Yeah? It means that there are no triangles in your graph. Okay. And for instance, if you say 3P1 free, so 3P1, that means 3K1, excuse me, 3K1, you take 3 vertices. And if you say 3K1 free, it means any 3 vertices you take, there must be at least one edge. Right? Because you want it to be 3K1 free, no 3K1. And 3K1 means 3 isolated vertices. So for instance, cycle on 5 vertices, it's 3K1 free. Any 3 vertices you take in a 5 cycle, there will be an edge between some of them, right? And the 6 cycle is not true. You take it just, no, it's trivial, right? So that's what this concept is. It's a big concept in graph theory. There's Fleischner, lots of results on this. And so Jörg Jochen and I, we looked at this from the perspective of these Hamiltonian problems. And there is this dichotomy theorem we proved like 2 weeks ago. We finished this. So let F be some graph. Now, this is an important class of graphs F that we're looking at. This P3 plus SP1. What does this mean? You have a path on 3 vertices. That's P3. And then you have here S copies of P1. So these are just K1, same thing, just points. Yeah? And you have S of those. So this is the graph we're looking at. And our Fs are some induced subgraph of this. Or not. Yeah? In this case, not. And then S is some integer. Then there is an infinite family of F3 graphs, each with 2 vertices between which there exists a unique Hamiltonian path. So you can find these graphs such that you have exactly one Hamiltonian path between some 2 vertices. Yeah? If F is not in here. But if F is an induced subgraph of this for some S, then there is a constant CS of this form here. This is Erdős second the proof. Essentially, this comes from that. Such that every F3 graph G having a Hamiltonian path between 2 vertices A, B contains at least then an exponential number. You see here 2 to the n over that constant distinct Hamiltonian path. And this will be really useful to build many Hamiltonian cycles. Yeah? I will explain a little bit. But we have this. And there is an analog of this for the Hamiltonian cycle setting, but actually there we cannot do a full classification. There are some cases which we don't know how to deal with. So it's not completely equivalent. But for the Hamiltonian path, we can do it. So a Hamiltonian path is just a path between 2 vertices which visits all the vertices. Right? It's just like a cycle, but it has 2 ends. And so here in the first setting, F not induced of this guy here, then you can have unique Hamiltonian path between some 2 vertices. If F is induced, an induced subgraph of this, then you have exponentially many. Yeah. So this is and there is nothing in between. Yeah. So either F is here in this case or in this case. There is nothing else than these 2 behaviors. And we now go on to one variant of this I want to focus because to motivate this a little bit. So what are these ST graphs? I think this is quite natural. I encountered this relatively recently, this definition, but I like it. So it just means that for every set of S vertices in the graph, it contains at least T edges. That's an ST graph. Pick one vertex there, one there, one there, one there. 4 vertices, your S is 4. If you're a 4,2 graph, there should be at least 2 edges in here. Yeah. And what I like also about this is, if you look into Hamiltonian problems, it's very difficult to control because your vertices can be, in some sense, close, but also very far. You can choose them. And you still have this density condition. Right? And now, there's an important connection because, yeah, in graph theory, it's a little bit dangerous. We can define many, many things and many are not so interesting. So let me just point out that the independence number of a graph is directly related to this. So what is independence number? This is an important parameter. So you have a graph and an independent set is a set of vertices, no two of which are adjacent. Yeah. And the independence number is how big can you make this set, this independent set. And the independence number is at most k if and only if G is a k plus 1, 1 graph. That's clear, right? Because your independence number is k. If you take one more vertex, well, there must be an edge. If there would be no edge, this would not be true. So ST graphs are just a generalization of this independence number concept, which is really important. And so Liu and Wang, and I'm sorry I couldn't find the first names. This is a paper in Chinese. Some people write C and J here, but I don't know what the first names are. So I couldn't write them, but I did what I could. It appears like so. And so for 2 connected 4-2 graphs are Hamiltonian. That's what they should. You have a graph. Okay, we need 2 connected. This is easy to see. So your graph can look like this. You have lots of edges here, but just one vertex here. This is not 2 connected. Yeah, this won't be Hamiltonian, right? So you need to put this 2 connectedness. This is the only. But then they say for 2 graphs, what does this mean again? Any 4 vertices you take, you have at least 2 edges in there. And they show that this is Hamiltonian. Again, we want to apply the meta conjecture. How many? How many Hamiltonian cycles must there be? And we weren't the first to have to pose this question. So actually, it was shown that they have ordered at least 8. They must contain at least 2 Hamiltonian cycles. But that's if you write a paper for every constant, then let's try to accelerate that process a little bit. Yeah, it wasn't so difficult in the end. I will. So what can we say about the number? Jochen and I proved quickly that this is an exponential number. So just to explain just what is the proof. So we already know that they are Hamiltonian. So you can imagine these graphs as a cycle, Hamiltonian cycle, just a circle, put all the vertices on the circle. And then you add chords, right? It has some chords, clearly. Because if it wouldn't have chords, it wouldn't be 4-2. You can just take any 4 vertices you take, there must be at least 2 edges between them, right? So that's okay. So you have a Hamiltonian cycle with some chords. And my intuition was, okay, I don't care. This is really difficult to control in a global sense. So let's just look locally. So we just start on the Hamiltonian cycle and we just walk along it. And my intuition was that at a certain point, yeah, if you walk along it for sufficiently long time, there should be more than one Hamiltonian path between the endpoints. Not just the original one you have, but also a second. And I thought it would be 8 vertices. Turned out that it's 9. But then you have 2, and then you get 2 to the power n over 9. Very, 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 really easy stuff. That was so okay. That's not really so interesting to publish. So we shifted our attention to this second question. So for some arbitrary constant c, does any sufficiently large Hamiltonian C1 graph contain a second Hamiltonian cycle? I let you look at it for a moment. So you can choose here like a million vertices, and you know that there must be an edge. One edge. But you do know that it's Hamiltonian. So again, the setup is cycle or the vertices are on it. But then you can choose a lot of vertices. Yeah, it's almost independent. But you do know there's one chord. Must there be a second one? This is, of course, yeah, like a Sheehan style question, right? You have one Hamiltonian cycle, is there a second? And we prove this. So S and T integers, S at least 2, T at least 1. If G is a Hamiltonian S comma T graph, G has at least this number of Hamiltonian cycles, 2 to the n, and this is a Ramsey number of S comma 3s plus 4. And so the Ramsey number, so connections to logic, but in graphs, this is for us r k comma x. This is the smallest integer n, so that any graph on n vertices contains either a clique of size k, that's just a graph on k vertices, such that all the vertices are connected to each other, or an independent set of size x. That's kind of the two extremes. Clique, all the edges, independent set, none of the edges. Yeah.
Where is T in this?
Just T.
So T does not.
T does not come. No. Indeed. Yeah. So we don't. Yeah. It's not. It's the minimum possible value. You know, that makes sense. Yeah. Because if you put zeros, then yeah, it means you have no edges. So that doesn't make sense. But indeed, it's then plays no more role. And should I show you the proof sketch or not? Maybe we don't do the proof. It's not a difficult proof, but we skip this. I wanted to show you this picture. You know, I tried ChatGPT, Gemini, everything to make a nice picture, but they failed miserably. to do a nice. So I had this picture, which
You succeeded.
I succeeded. But yeah, it's not so difficult, but they did a terrible job. It was not like, okay, fix it now. But yeah, you can show this theorem, and you can do some more stuff here. I don't want to tell you anymore. I want to get to the third part, then we can conclude. Because there's actually, from all of my talk, if you want to remember one sentence, I haven't uttered it yet. So I would like to, yeah, and then we can close. We have heard enough. So Hamiltonian cycles and squares of graphs. So let me just give you the definition so you understand what I'm talking about. So you have some graph here in black, PS, and then you define the square as adding to G. So you take G and you add to G an edge between any pair of vertices at distance 2. Yeah, so for instance, this guy, 1, 2, you add an edge. So the square of the black one is black together with red. Is that okay? Yeah. So this is basically the only definition that you need here too. And then there is a celebrated theorem of Herbert Fleischner, who showed that the square of every 2 connected graphs is Hamiltonian. So you start out with something 2 connected. You need that. Again, some easy observation. You need 2 connectedness. You take the square. You get a Hamiltonian cycle. How many? And then, yeah, many proofs exist of this. This Georgakopoulos, essentially, this is for me a book proof. It's a really beautiful proof, but many intermediary things existed. And then there's an algorithm also to do this. I should point out that if G is Hamiltonian, it's easy to see that G squared contains 2 to the omega n Hamiltonian cycles. Why? So again, if G is Hamiltonian, this means, so you have a graph, and you know that there is a Hamiltonian cycle, right? Lots of other edges maybe, but you know that there is a Hamiltonian cycle. Right? Okay. So I stand on the Hamiltonian cycle, and I go A, B, C, D. 4 consecutive vertices. But in the square, I can also do A, C, B, D.
T.
You agree? So you get exponentially many. You have all these switches, right? So this is really easy. But this is one of the things we use, and it's enough. So this is the main theorem. So we have 2 to the n over 50. This is joined Solomon Loken, Ozeki, Carsten Thomas. And we're still polishing some things, but yeah, we have proof now. But yeah, but this is just what I wanted to leave you with. So the theorem of Fleischner tells you this with the 1 here, yeah. Without you don't need this. So if you take a triangle, it's not true. But anything bigger than a triangle, it's true. So Fleischner says here a 1 here, and we say 2 to the n over 50. So the growth is exponential, at least exponential. And you can show that it's asymptotically sharp.
For the numbers in between, I mean, for small numbers, is n over 50. You're only interested in the n greater than 50 here, obviously.
Yeah, indeed. So asymptotic. We're interested in the asymptotic behavior. You can improve this somewhat. The over 50 here. It's not. Yeah. We didn't try to do that so much to optimize this. We rather try to give make the proof as elegant as we could, and that was the main priority, and get the asymptotics right. That was the main point. And yeah, there are 2 cases, but I want to stop here. So if you want to remember anything from my talk, it's this one, that Fleischner. This theorem of Fleischner actually has this enumerative extension that you can do actually exponentially many cycles in squares of 2 connected graphs. Thank you very much for your attention.
Thank you, Carol. Any questions for Carol's talk?
So,
Yeah.
If you can show me what you wanted pretty completely for the picture, I have some skills.
Okay, thank you very much. No, I can also, I wanted to be efficient about it, and nowadays you just put everything into the large language model, and but it failed so miserably with this. I don't know why, but yeah. No, thank you. Yeah.
Oh,
I want to give this talk I will be in Chennai in a few days, and I want to give kind of this talk, but I saw today that it's much too long, so I will try to make a nice figure.
I have a question. I'm a question person. So, if you talk about 4 connected cases, 2 connected cases, is there any special interesting, anything special interesting for 3 connected graphs?
Yeah, I mean, there is a subfamily here, right?
Yeah.
So you can also take squares of 3 connected graphs. Yeah. There are some problems on 3 connected graphs, definitely, especially planar 3 connected graphs. Yeah.
For example, like this G square graph.
Yeah.
Like the square graph, like if you have 3 connected or even 4 connected, will the number of Hamiltonian cycles also be exponential things, or?
Yeah. If your connectedness is just some constant, yeah, it will just become denser. So the problem will become easier. Right? You need to be careful when you get close to complete graphs. I mean, they have many Hamiltonian cycles. So just in the sense that you are not adding many edges by taking the square, because there are not many edges to, but they have many Hamiltonian cycles anyway. So that's yeah, but for the rest, yeah, if you increase here the connectedness, then it makes in some sense the problem easier. Yeah. So and you cannot decrease it, as I said. So
actually, I also think about the connected graph. I think at the very beginning, I thought maybe if we do G square for some connected graph, it could be Hamiltonian, but actually, I think it may not be correct.
Yeah, but it's true. In some cases, it is definitely. So it's just when I meant by that there exist connectivity 1 graphs, which square of which is not Hamiltonian. But then there is a nice paper looking at the circumference. So that means the length of the longest cycle. So you can find quite long cycles, but not quite n. So yeah.
Thank you. Any other question?
How many I think for this complete graph where every two are connected, you say they have a lot, how many would they have?
I think it's some factorial, yeah. I would guess, because you can choose, right? You start somewhere. I don't know by heart, but you start somewhere.
Yeah, okay, that should be easy.
Should be easy, should be easy. And these are, but you can think of almost complete, and then you can see that what is interesting about them is that there is not a big difference in the number of Hamiltonian cycles they have and their square has, because you don't add a lot of edges. Here, our intuition is, yeah, we add lots of edges, so the number of Hamiltonian cycles increases very much. Just take one Hamiltonian cycle. It had just one. And then you do the square, and you have this exponential number. So it explodes. Right? But for things that are very dense, yeah, it's a bit different. So one could also look at that difference function, but that's a different problem.
Any question? No, I think no more question. Oh, good. Then let's thank Carol again for the talk.